Alrighty, everybody. It's 4, so we're gonna go ahead and get rolling. This is the circuits exam review. Make sure you're in the right spot. This is hosted by IEEE HKN. So IEEE is an organization for computer engineers. If you haven't heard of them, we have a lab here. Check them out. We're on your lab assignments outside of office hours and own. And then HKN is a subset of IEEE. We're an honor society. So we take a certain proportion of like the top students in each grade. You'll get an invitation from the advisors if you want to join. And we just put on a lot of volunteering outreach events, sort of like this. Looks great on a resume, really good networking opportunity, leadership opportunities. So if you see that and you're interested, just know that that's us and you're welcome to join. That out of the way, we're just going to go ahead and get started. We have 8 problems and there's 4 of us here, so we're just going to take 2, work through them. You guys can ask questions throughout, and hopefully this will be helpful for you guys. And then if I ever need to slow down or speed up or speak up, just yell at me. And then a common problem is sometimes stuff is not visible because I'm not paying attention. So just yell at me if I need to move the page, okay? So the first problem, question 1, just asks us for the voltage from node 1 to node 3. That's this voltage here. And it also asks for the current from node 5 to node 4. That's this current here. That current, and we want this voltage. Since we know this resistance is 91 and we know the current this way is negative 9.1 milliamps, the voltage drop across this resistance is pretty straightforward. It's just an Ohm's law equation. This voltage drop is the current across this resistor. Again, our current is 9.1 milliamps and our resistance is 95 ohms. Punch that into your calculator and you get negative 0.828 volts or 828 millivolts if you prefer that. And so that is our answer for question 1. Pretty straightforward. Now for question 2, we want this current. So you know this current enters node 3. We know this current exits node 3, and this current is also exiting node 3. I'm just gonna label these 1, 2, and 3. So we know that the sum of the currents entering any given node has to equal the sum of the currents exiting the node. So current 1 is entering, and that has to equal currents 2 and 3 since those are exiting. This one that we want to solve for is I3. So I'm just going to rearrange this to solve for I3. There you go. So we have 2. And then we just plug in our values. 9.1 milliamps minus negative 9.2 milliamps. Punch all that into the calculator and you should get 0.1 milliamps. So 0.1 milliamps is going down from node 5 to node 4. And that's our answer for part 2. Everything there makes sense?
Give us a little time in the beginning to draw the diagrams.
Oh, sure thing. Yeah, I'll leave this up.
Is this formatted the same as the actual exam, or is there gonna be stuff on the real exam that's not on here?
So these questions were pulled from past semesters, back when it was circuits 1. So the formatting might, and these are also from a different professor, so the formatting might be a little different, but overall the content will be the same. All right, everybody good to move on to question 2? Awesome. Here's question 2. I'll give you guys a moment to look it over, write it down. So this one is asking for the voltage from node 1 to node 0, and is asking for the current from node 2 to node 3. So for this voltage, from node 1 to 0, I'm going to have to find the voltages across these 2 resistors, right? Since I can't calculate across this source, we got to work with the resistors. And we have the current through this resistor, but we don't have the current through this resistor, and we need that to find the voltage. So I'm actually going to start with the second part of the problem, because knowing this current will allow me to calculate this voltage, which will allow me to calculate the total voltage drop. So we're looking for the current from node 2 to node 3. And we know that this current is entering node 3. I'm going to call that current 1. This one is also entering node 3. We can call that current 2. And this current is also entering node 3. And I'll call that current 3. So the sum of the currents entering the node, all 3 are entering. So we have I1 plus I2 plus I3 equals the sum of the currents exiting. There are no currents exiting, so we have 0. We're looking for this current 2, so I rearrange this. I2 is equal to negative I1 minus I3. I'm going to plug in my values here. I1 is negative 7.6 milliamps minus 8.8 milliamps. Plug all that into your calculator, and you should get negative 1.2 milliamps. Negative 1.2 milliamps flowing this direction. So that is our answer to this second part. So now back to the first part. We want the total voltage from node 1 to node 0. So I'm going to call this voltage V1 and this voltage V2. I'll sum them together and that'll give us our total voltage drop. So V1 is this current times this resistance. V equals IR. And that is equal to negative 7.6 milliamps times 93 ohms. And that is equal to negative 0.7068 volts. So that's our voltage from 1 to 3. Now we need our voltage from 3 to 2. That's what I called V2 earlier. But since we want it from node 3 to node 2, we're going to have to flip this current, right? Because this current is flowing from 2 to 3. We need it to go the other way. So we're just going to put in a positive 1.2 milliamps just to get it facing the way we want. Our resistance is 63 ohms. Punch that in the calculator and it's 0.0756. So from node 1 to 0, the 1 to 0 is equal to V1 plus V2. We add these two together and we get negative 0.6312 volts. That's our answer to the first part. Yes.
Could you have gone about this by just simplifying the circuit, like adding two current sources together, and then since the two resistors are in a series, adding those together and solving for voltage?
You could have, yes, because this. Let me think about that one. Well, these two sources aren't in parallel, right? Because this connects to this node and this this one connects to these two nodes. They share the same bottom node, but because of this, they're not exactly in parallel. So. Any other questions? All right, I will pass it on to Ryan.
There's a moment to draw that circuit if you'd like. Right, so the first part of this problem asks us to find the voltage across this resistor. Now, it doesn't specifically state a polarity for us. So in this case, I'm just going to arbitrarily choose from node 3 to node 5 here as the voltage across the resistor. You can do it the other way, and all we do is just change the sign of your voltage. So if we start here, and we work around this way, counterclockwise from the circuit, we first encounter this voltage source. So we have this voltage source between node 3 and node 1. So we have V31. As we keep going, we can enter the negative side of this voltage source. So then minus, in this case, V10. And as we keep going, we enter the negative end of this voltage source. So minus V45. And that ends up equaling the voltage across resistor here, V35. I like to break it up into this. That way I don't get mixed up with any of the sign conventions. Because, for example, we enter the negative end of this source, and it's a negative voltage. So when we plug in the numbers, we have 8.3 for this first source, minus, then we have a negative 8.7 for this next one, minus, again, we enter the negative end of this source. So we have a minus, then negative 8.8. It's equal to V35. So now when you solve this, you can see that our voltage, V35, is equal to 25.8 volts. Again, I know this is pretty simple, but I think it's good to kind of show when you enter the positive versus negative end of your source, what you then have to do the values. Again, I like to keep it, if you enter the negative end of the source, you subtract, and then whatever that value is. I tend to keep it as a variable when I set up my equation, that way I don't lose a negative sign anywhere. So now I'm asked us to find the current through the circuit. In this case, let's go through this resistor here. So we have I35 is equal to the voltage across our resistor, E35, divided by our resistance. Plugging in the numbers, we have 25.8 volts divided by 58 ohms. And that gives us 0.4448 amps, or if you convert that into milliamps, 444.8 milliamps. Any questions? All right. Give you guys a moment to draw the circuit. All right, so the first thing that this question asks us for is to find the equivalent resistance of the circuit. I'm just going to name that R equivalent. Now, starting here by the source, we've got a resistor of 43 ohms. So I'm just going to add this right here. Plus, now we hit the resistance over here. Now, this 79 ohm resistor is not, you can't just add it to the system because you have all of this resistance over here also connected between those two nodes. So we'll have to break it up. So we have 79 ohm resistor, and that will be in parallel. I'll just do this symbol way down to the node, in parallel with the series combination of this resistance, 85 ohms, and the 73 ohm resistor in parallel with these two. That sounds a little complicated at first, but I'll try and break it down the best that I can. So we have that 85 ohm resistor plus, now if we look over here, this 73 ohms, again, you can't just add it directly in series because we have this other path that current takes. We have to account for those resistors. So we have that 73 in parallel with, in this case, the 96 and the 90 ohm resistors are in series. So we can just add those together. 90, 96. And then finally, as we finish going around the loop here, we have the 71 ohm resistor that's in series with 43, and then this giant equivalent mass. So now I'll go through and I'll solve it and I'll break it down step by step. So first, when we're looking on this end, we see that we have two resistors in series, so we can just add those together. That's not 99, that's 96. So when we add these two resistors together, simply, we get 186 ohms. Now, this equivalent resistance here is in parallel with this 73 ohm resistor. So if you now take a look at this section, 73 is in parallel with 186. Now, if you have two resistors in parallel, you can write it in the form of the two resistances multiplied by each other, divided by the sum of the two. This expression is equivalent to 1 over R1 plus 1 over R2. It's important to note that if you had three resistors in parallel, you can't just multiply by a third one and then add the third value here. It doesn't end up working this way. This equation right here is just a shortcut for using two resistors in parallel. You can, however, simplify two resistors and then make that value in parallel with the third one. It just depends on how you want to break it up. This equation, however, you can keep on adding 1 over R3, etc. You can keep adding more resistors to that. That equation will always be true. This one is just a shortcut for two to make it a little faster. So when we solve this equivalent resistance here, we end up getting 52.4247 ohms. So now we have an equivalent resistance between those 5 and 4 here. So now, looking back at this, we now have our 85 in series with our 52.4247 ohms. And that gives us a resistance of 137.4247 ohms. Now we know what the resistance between 5 and 2 are, or you can say 3 and 2 along this leg. So again, breaking it down, in that parallel, we have 79 in parallel with that 137 ohm resistor. When we write that out, we have 79 ohms times 137, 247, divided by 79 plus 137.427. And that gives us a resistance of 50.163 ohms. So this resistance now accounts for all of the resistance values between node 3 and node 2. Now we have that, we can simply add our equivalent resistance here with the other resistors. So we have our equivalent is equal to 43 plus 50.6318 plus 71. That gives us a total equivalent resistance of 164.16. Any questions on that first part?
Could you just go over again how you like set up the initial equation for the like which ones were parallel in series?
Yeah. So I know when I first started, it was hard to look at it in the way that I set it up. Another way you can do it as well as you're confused is you can start on this other side. But essentially, what I did this time, starting from our node 1, we have 43 ohms, so we just write 43. And now when we hit node 3, we can go down here. We have the 79 ohm resistance, but current doesn't all have to go through that resistor. It can go down this way to node 5, and it can break down this way and break down from 5 to 4. So now that this 79 ohm resistor is going to be in parallel with an equivalent resistance over here. And when we break that down, we end up having this 85 in series with. So if we work the other way, which I think would make more sense to start off with, that's what I started to learn with. Looking at it, we have this 96 ohm resistor in series with this 91, right? So we can have an equivalent circuit. If we ignore all that with this 186, those are in series. So now when we look at it coming this way, we have this 186 ohm resistor, and that's directly in parallel with this 73. So now we can solve that equivalent resistance. So we solve for a new one. We can draw, let's say, a new circuit through here. And this is then that 52 ohm resistance. Now, as we keep coming this way, we have this 52 in series with this 85 resistor. All right, so now we can add those together. And now we have a new resistance that describes all of these together in parallel with this 79. Then we can just find what the parallel equivalent resistance is between those two resistors. And now we have one that we can use to solve that's in series with these other ones. Does that help a little bit?
Thank you.
Okay. Any other questions? All right, so the second part of this question asks for the current from node 5 to 4. Now, there's multiple different ways you can solve for this. I don't know if Professor Hassel talked about using ad hoc methods. You can still break down the circuit and solve it that way. I'm going to solve it using mesh current. I feel like that's a pretty straightforward method that you can use on any circuit, and you're less likely to hit like hiccups in there, like messing up with a resistance somewhere. So with mesh current, I'm going to define our current loops, I1, I2, and I3. So I can set up my first equation going around loop I1 here. So I generally start in the bottom left corner. You can start whichever you would like, as long as you remain consistent. We'll find out if you solve. So I tend to start in the bottom left corner, then I go around clockwise. So in this case, we have the negative side of this voltage source. So we have minus the value of the voltage source, 8.2 volts. As we keep going, now we have the voltage drop across this resistor to account for it. So that's plus I1 times the resistance, 43. Plus, as we keep going around, we want the voltage drop across this resistor right here, and that is equal to I1, our current flowing down, minus the current that's flowing the other way, as we have described it. So minus I2, so that's the total current flowing in this direction, times the resistance of 79. And we add that to the voltage drop from node 2 to node 0. Then I1 times our 71 ohms. And that has to be equal to 0. So now I'll do our next equation. In this case, I'll just follow along I2 here. So for equation 2, starting at node 2 and going up, we have I2 minus I1. That describes the current then that's going from node 2 to 3. Times the resistance, 79. We come around, and now we have the voltage drop from 5 to 4. So we have I2 minus I3 times our 73 ohms. Plus this voltage drop right here, which is then I2 times 85. And that has to be equal to 0. So now for our final equation, equation 3, we're going to follow along the mesh of I3. And so we have I3 minus I2 times 73 plus I3 times 96 plus I3 times 90. Now, if you want to save space, you can also write this together as just an I3 times 96 plus 90. And that'd be equivalent to this, these two factors right there. All right, so now you can use whatever sort of solving software you'd like. You can try and solve it by hand. It's a three equations, three unknowns, it's a little complicated, but you definitely can solve it by hand. Solving your calculator, set up as a matrix. I like to generally solve using Mathematica. So first thing I generally do is I make sure I clear my variables. I'm looking at software. Now, when you're doing it, depending on your problem, you might be able to set up different variables in here, which is definitely helpful when you start getting to AC systems. You can set up your voltage sources, your current sources, you can set that all up beforehand. In this case, since it's fairly simple, I'm just going to start writing the equations. So I'm going to write in our equation 1, and that is equal for negative 3.2 plus I1 times 43. Plus I1. That's then equal 0. So that's setting up our first equation in Mathematica. If you guys haven't used Mathematica much before, when you're setting up your equation, you just use the single equals mark. And then in your equality here, see it at the moment, but how we had this entire equation set to 0, within your equation, you then use two equations. Essentially, we're setting like the variable equation 1 to be this expression. So now we look at equation 2. Type that in. 2 minus 1 times 9 plus 32 plus 5 times 3 plus 5. Equation 3. I3 minus I2 times 3 plus row 23 times plus. That is all. So now all we've done is just put the equations that we've already solved for by hand on paper into Mathematica. So now I set answer equal to solve, and then I make Mathematica solve for equation 1, equation 2, equation 3. for I1, I2, and I3. And in this last line of code, I like to just pull the variables out of that so that if you wanted to in the future, you can then use these variables to solve for other things. So we have I1, I2, 3. And that should then solve for our currents. So this is broken up here. We have I1 here, I2 here, and then I3. So I'm going to write those down really quick. I1 is equal to 49.95 milliamps. I2 is equal to 18.23 milliamps. And I3 is equal to 5.14. So now we have all the currents as we have defined them in here. So the final step then is we need to find the current from node 5 to 4. That's this current right here. So I4 is just equal to I2 minus I3. Ends up being 18.23 milliamps minus 5.4 milliamps. And that gives us 13.09 milliamps. Any questions? Okay.
All right. So
I'll be back here. Cool. All right. So I'll give you guys a moment to copy this down. So when I'm looking at this problem, the one thing that's screaming out to me is using node voltage. We could use mesh current if we want to. We would have 3 meshes, one here, and one here. I just feel like using node voltage. So I'm going to be doing that. So I'm going to create a node equation at node 4, at node 1, and at node 6. So I'm going to start out with node 4. And I'm just going to be looking at the current outflows at each branch right here. So the first one right here would be negative 0.05 V21. I'm not going to worry about what V21 is right now, but if you're looking ahead, you'll notice that it'll simplify to something very, very nice. I'll add that with the current flow going down from 4 to 6. So that'll be V4 minus V6 over 75 ohms. And I'll add that to the current flow going down here to here. So that'll just be V4 over 95. And all of that from KCL will equal 0. Now, substituting V21, we'll see that the voltage from 2 to 1 right here, that's just a short, which means that the voltage has to be the same, which means that this term right here all goes to 0. So that right there, that is our first node equation. I'm going to move on to node 6.
So we'll start out with this current flow going from 6 to 5. I'm going to, I probably should have said this earlier. I'm going to set this whole bottom rung here, 0, 3, 5, to be a ground reference. So that'll mean that V3, V0, and V5 will just be 0. So I apologize for glossing over that. That's why we would have a V4 over 95 instead of V4 minus V3 over 95. So anyway, back to the node 6 equation. We would have the voltage drop from 6 to 5, which is just going to be V6, because V5 will be 0 from that ground reference, divided by our 64 ohms. We'll have the current flow from here to here. So that'll be V6 minus V4 over 75. And we'll have the current flow from 6 to 7 to 2 to 1. So since 6 and 7 are at the same voltage and 2 and 1 are at the same voltage, this will be the same as V6 minus V1, because I really only care about the node voltage at 1, divided by the resistance in that path, so 53. And all of that's going to be equal 0 from KCL. So our final node equation will be at node 1. So the current outflow going from here to here is completely constrained by that current source. So I'll just be negative 6.2 milliamps. The current flow from 1 to 4 is going to be the negative of negative 0.05 V21. So that'll just be positive 0.05 V21. And then we have the current flow from 1 to 2 and then 7 to 6. So that'll be V1 minus V6 over 53. And all of that is equal to 0. Now again, we have this V21 term floating around here. 2 and 1 on the same node, which means that this whole term just goes to 0. So these are our 3 node voltage equations. And coming up with that, do you guys have any questions? Sounds good. So to actually solve this out, I'm not going to do it by hand. I'm going to have Mathematica do it for me. So I'm going to get that open really quick. Cool. So right here, the 3 unknowns we have are V1, V4, and V6. So for our first equation from node 4, we have V4 minus V6 divided by 75 plus V4 over 95 equals 0. Second equation is from node 6. So we have V6 over 64 plus V6 minus V4 over 75 plus V6 minus V1 over 53, all equal to 0. And our third equation would be negative 6.2 milliamps plus V1 minus V6, all divided by 53 equals 0. So I'm going to steal the code that Ryan wrote, because I don't feel like writing it myself, and just plop it at the end here. Take this V1, V4, V6. There we go. So what this is telling us is that V1 is equal to 616.87 millivolts. V4 is equal to 161.09 millivolts. And V6 is equal to 288.27 millivolts. So I'm going to get that all written down and switch right back to the document. Ooh. So from all this, V1 is equal to 16 volts. 4 is 169.9. 6 is equal to 288.27 volts. So the first thing we care about is for actually solving this whole thing out is the voltage from node 4 to node 6. So that is just going to be V4 minus V6. So when we actually compute that, that'll be 161.09 minus 288.27 millivolts. And that is equal to negative 127, excuse me, 0.18 millivolts. The second thing we care about is the current going from node 1 to node 2. So there's a few ways we can do that. The first is we could go through and do V6 minus V1 divided by those 53 ohms, and that'll give us the current flowing from 2 to 1. Flip that around, we get the current from 1 to 2. We can also use KCL here, just given what we know. So I'm going to do that. So I know that I12 plus I14 plus I10 is equal to 0. So we're just applying KCL at node 1. I'm going to substitute in values. So that tells us that I12 is equal to, plus 0.05 V21 minus 6.2 milliamps is equal to 0. Again, V21 is V21 is equal to 0. So this term right here goes to 0, which means that I12 is equal to 6.2 milliamps. So with all that, do you guys have any questions? Sounds good. Moving on to question 6, and I'll give you guys a second to copy this and then again. Okay, so when I'm looking at this one, again, we can do node voltage here. It just wouldn't be too pleasant. We have 1, 2, 3, 4 nodes to consider, and we could combine 3 and 5 into a super node, but that's just more stuff to keep track of. So I'm going to elect to use mesh current for this one. It's very nice. We have 3 loops right here that we can throw stuff in, so I'll be doing that. I'm going to consider this one I1, this one I2, and this one right here, I3. So our first equation is going to come from this cell right here. So from loop 1, we get that I1 is constrained immediately by this current source. So that's really nice. We're told off the bat that I1 is equal to 6.3 milliamps. On our second loop right here, I'm just going to go around the loop and use KVL. So starting right here from 2 to 3, you have the voltage drop from 2 to 3. That is going to be the currents flowing here, which is going to be I2 minus I1. And multiply that by those 54 ohms. We're going to get the negative of this voltage source. So we'll get plus 6.3 volts. And then I2 minus I3 to get the current going from 5 to 4. Multiply that by that resistor. And set that all equal to 0. So for our final loop, we once again have this current source constraining what our current is going to be. So I know that I3 is moving the opposite direction of this current source. So that's going to equal 0.05 V50. That's great, but now we need to know what V50 is. So that is just going to come from the just voltage drop from here to here. Setting all of this equal to a ground reference, we know that this whole thing is going to act as one node. So V50 is the current flowing here down. So I2 minus I3 times those 84 ohms. And that right here are our four equations. We have four unknowns, even though V50 is kind of already defined in terms of our other unknowns. So those are the equations we need to solve this thing. Does that make sense so far? Sweet. So bouncing right back to Mathematica. We care about I1, I2, and I3. So our first equation is just I1 being directly equal to 6.3 milliamps. Equation 2 is I2 minus I1 times 54 plus those 6.3 volts plus I2 minus I3 times 84, and all of that equal to 0. Equation 3 is our other constraint equation. So I3 equals 0.05 times V50. We also need to care about what V50 is. So that is going to equal I2 minus I3, that quantity, times 84. I don't know if Mathematica will get mad at me for having V50 after I use it, so I'm just going to throw this up here. And then we'll just solve these systems. Cool. So that is telling us that I1 is equal to the 6.3 milliamps, which we expect. We know that directly. I2 is equal to negative 84.95 milliamps. And I3 is equal to negative 68.62 milliamps. So I'll get that written down on the page and then move it over. All right, now we can actually solve some of the stuff that we're asked to solve. So the first bit is going to be the voltage drop from node 4 to node 5. Is that right there? V45. It says V54 up there. Same magnitude. It'll just flip the sign. So I'm going to scratch this out and say V45. And that is going to equal the currents flowing up from here to here. So that is equal to I3 minus I2 times the 84 ohms. And that right there is going to give us 1.37 volts. The second bit is the current moving from node 3 to node 5. So right up here, that is the current flowing this direction. That is directly going to be equal to I2. So I35 equals I2, which equals negative 84.95 milliamps. And those are our two answers. Any questions?
If there was a current source that was part of two loops,
Yes. Oh, okay.
what would happen? You have to consider both loops sharing that source.
Yes, I think one of the questions later in here has something like that. But sketching it out really quick. Let's say that we have system, I'll put a resistor here, make it current source. I'll say that's just I0. So if we were to do mesh current on this system down here, if I said that this was I1 and this was I2, our first equation, if we wanted to concern ourselves with that current source, is that the current moving from this node to this node is equal to I0. So that will be equal to I1 minus I2 equals I0. So that current source is shared just by both mesh currents. And then if we wanted to solve out this whole system, we could do the loop on the outside, because I2 doesn't really give us any useful information from its loop. I2 is just telling us the relationship to the current source. So we could just have I1R equals 0. We would probably not have that really be the case. But yeah. So is that making sense? Sweet. Any other questions? Sounds good. All right, I'm going to pass it off to Megan, who is going to do questions 7 and 8. Do this. Joe, I know. Oh, 7. This is 8. Here we go. Cool.
So we're trying to find the voltage from 104 and then the current. I'm just marking that and then I'll let you guys draw the circuit a little bit.
Okay.
So how I'm going to do this, I am going to do mesh currents. So I am going to have a loop on this inside box, we call that I1. And essentially a loop around this L. We're going to call that I2. Also, I am left-handed, so if like my hand starts covering the paper and you guys can't see, please let me know. I will try to move my hand so that it's easier for you guys to see. All right. So with doing this mesh current, we noticed one major problem with having these two boxes, like the two loops as they are, is because of that current source, the negative 6.3 milliamps. So that is actually going to be our first equation. So we're going to say EQ1, and that's going to be that negative 6.3 milliamps is going to be equal to I1, because we have this current flowing that way. And then I2, which is this current going that way. So minus I2. And since we need to have two, like, because there's two boxes or two rooms, we need to have two equations. And so we can't go through any equations that have the like loops touching that current source again. So what we're going to do is we're going to go around the entirety of the circuit. So for our second equation, we're going to do EQ2 is going to be equal to 48 ohms. And that is going to be times I1 plus 90 ohms times I2 plus 8.2 volts plus 90 ohms times I2. And that is going to be equal to 0. Does that make sense how I kind of went around the whole circuit and just followed the currents and the paths that they took? So like for this one, it's only getting touched by I1. So we only have to worry about I1, whereas like these two are only being touched by the I2 circuit. So we have to worry about those. Actually, with how I have this defined, it would be a negative I2. We will be using our favorite linear algebra tool, which mine also happens to be Mathematica. So we're first going to clear all our variables. So I'm going to call I1, I2, Q1, and Q2. And so I'm going to write EQ1 is equal to negative 6.3. And I'm just going to divide it by 1,000 just to get it to the negative, to like the milliamps into amps, is equal to I1 minus I2. EQ2 is equal to 48 times I1 plus 90 times negative I2 plus 8.2 plus 90 times negative I2, and that's going to be equal to 0. And then we're going to put that into our solve function. And we're going to have that be EQ1 and EQ2, I1 and I2. And so then, if we want to get that into nicer formatting, so we don't have just a bunch of decimals, and I am so sorry, I forgot to put that onto the screen for you guys. You can do, right there, engineering form, and then it'll put that into, and then it'll put it into like standardized engineering units, so like your milliamps, micro, nano. So normally to the powers of like -3, -6, -10, it'll put into those forms so that it's easier. So now we can say that our I1 is going to be 53.53 milliamps. And our I2 is 59.83 milliamps. You know, rounding, truncating. I normally take it to like 2 decimal places out if I'm just giving answers, because that's what most professors like to see, is like 2 decimal places. So that's good news. We figured out nodes from the current from node from 2 to 6, because that's just going to be the opposite of this I2 here. So I2 to 6 is opposite of I2, which means that's going to be negative 59.83 milliamps. And does that make sense why I'm saying it's the opposite? I'll take that back. I'm saying it's the opposite because if I'm saying that the current is flowing like that way, but then I'm looking the opposite direction, we need to flip that sign. And then if we are looking for the current across from 1 to 4 here, so 1 to 4. Lord, I keep repeating the line. I'm sorry, the viewers council was loud. We're going to say that's going to be 98 ohms times I2 minus I1. Does that kind of make sense? Because we have I2 going on the positive side and out the negative, and then we have I1 coming in the negative going out the positive. So if we do that, I'm just going to type it in mathematical real quick. Sorry, I am doing that. No, I love when I can type fast and then everything goes to shit. So you get 620.4. Hello. Volts, which is indeed correct. Does everyone understand how we got those two answers and how we like kind of worked through the problem? And now let me see if I can find the question. I'll let you guys draw this one real quick. All right. So we're trying to find the current from 6 to 3. So I 6 to 3 and current from 2 to 1. So with this one, again, I would recommend using mesh currents, mainly because it is a bit simpler than doing your node voltage, because you would have 5 nodes in this case that you would have to try to solve. Whereas you would only have 3 loops for your current. So you're going to have a current here. I'm going to call that I1. You're going to have a current here. We're going to call that I2. And then we are going to have a current here. And we're going to call that I3. Like before, we have a current source. So that will be automatically our first equation. Because when you see a current source, just automatically assume that you have an equation already solved for when you do mesh currents, because you have 2 boxes that are meeting each other forming that current. So it's a really simple equation to do. So we're going to have equation 1, and that is going to be 7.1 milliamps equals I1 minus I2. Then for our second equation, I'm just going to do this little box down here because it's the next simplest one that we can do. So this is going to be I3 minus I1 times 55 ohms plus I3 minus I2 times 45 ohms plus 67 ohms times I3. And that is all going to equal 0. Does that make sense how I did that equation? All right. So now for our last equation, I'm going to do around the entire loop like we did the first time. So we're going to have negative 6.2 volts plus 70 ohms times I1 minus 0 minus a negative 0.08 volts from 0 to 1, which we'll come back to, plus 84 ohms times I2 plus 47 ohms times I2 plus 67 ohms times I3, and that's all going to be equal to 0. Also, I'm sorry for running out of room there. So we kind of got lucky that our dependent voltage source is dependent on our independent voltage source, because we have from 0 to 1, so 0 to 1, that's directly over that voltage source. So we can say equation 4 VO0 is equal to a negative 6.2 volts. All right. And so then we're going to use our favorite linear algebra tools, and we're going to solve for all the currents, which would essentially get us all our answers. So let me So like before, we are going to clear all our variables. So I1, I2, I3, and then I'm going to clear 1 to 0, or 0 to 1, just so that I can keep consistent with what I have written in my notes. And then we're just going to clear the answer functions as well. So if we start to type in our equation, 1, 3, so 3. Plus 67 ohms times 3, and that would equal to 0. Our third equation equals 367. I2 37 times I2 plus 67 times I3, and that is equal to 0. And then EQ4 is going to be equal from 0 to 1 equals negative 6.2. And like Joe said before, Mathematica might get a little mad if that is below that one, so I'm just going to put it in just to make the program happy. But then we can write our solution of Q1, Q2, Q3, and Q4. And I did the thing. And we can do I1, I2, I3, and the 0 to 1 just to make it happy. So it's mad at me because I didn't put the double equals here. So if you find like errors in the Mathematica code, make sure you write the double equals to like saying, oh, this equals this, not like saying, oh, this is a name to the equation. So by doing that, we get our currents to be that. Make sure that on the page for you guys. It's 32.15 milliamps. I2 equals 25.06 milliamps. I3 equals 17.34 milliamps. All right. So then we can say the current from 6 to 3 is going to be equal to I3, which is 17.34 milliamps. And then the current from 2 to 1 is going to be the opposite of I1, which is negative 32.15 milliamps. Does that make sense? Are there any questions for me? All right. So, like Jacob said before, we are IEEE HKN. We will be hosting review sessions for you guys throughout the course of the semester. And if you know anyone that is in your class that would benefit from coming to these sessions, direct them to us. Also, if you have trouble throughout the semester, you can reach out to Jacob or myself or anyone on the HKN leadership team, and we can connect you with people that can help. Otherwise, the ECE Learning Center, located in ERC 123, is also a very great resource to use. We are recording these. It's not obvious from the screen right now. This will get emailed to your professor probably sometime tonight or whenever we get, it all edited and everything. And he'll send that out to you guys so that if we say something or you want to watch how we do Mathematica again or something, you can go back through the video and if you have any questions for us that you don't want to ask in front of the group, you can come up to us and everything. But otherwise, have a great night, and we wish you well on your exam.